So in our last video we have observed that ideal transformer is almost like a conducting means a pair of conducting wire except we can have in case of conducting wire you can't have different voltage level and electrical isolation. Here you can have different voltage level across secondary, and also you can have that electrical isolation. But other than that, it is almost like a pair of conducting wire, pair of pure conducting wires that are made up of ideal conductor. Like if you connect an ideal transformer with your source, if this is my ideal transformer here, instead of transformer I would like to draw it like a two-port network. So here if you connect it with a source, you connect primary with a source, the current drawn by this transformer is zero, almost zero. Power drawn by the transformer is zero. And when you connect any load with the secondary, depending on the nature of that load, if this load draws a current, say 5 ampere, and if your transformer is a transformer with 2:1 ratio, then here your current will be exactly 2.5 ampere. And if you have 1:1, then just like a pair of conducting wire, like whatever current is, if you place a pair of conducting wire here in this inside this box, then there will be connection, and if it is 5 ampere, it will be 5 ampere. Whatever power factor you will connect across this secondary side, you will get the same power factor across your load. But in case of 1:1 transformer, what you are having, and in addition, you are having an electrical isolation. It is not connected. There are coils, but they are not connected. However, the power factor of the load is, and power factor across source is exactly the same. So now let us gradually remove the idealistic assumptions and see what we are getting here. So first let me remove that constraint that permeability is close to infinity, or value of permeability is close to infinity, and value of reluctance is close to zero. Now instead of that, in case of a practical one, we will use core material with no reluctance, but not zero reluctance or almost zero reluctance. So how this Means from zero, almost zero reluctance to low reluctance will change the phasor diagram. See here you will have V1. Here you are having okay, before drawing that E1, let me so now when it was I was show you in some slide that flux is equal to mmf by reluctance. Now when this R was almost zero, then you need almost zero, and although I told you that this 0 by 0 makes no sense in mathematics, but we are engineer and we are empowered to means claim, assume, manipulate things according to our own requirements. So 0 by 0 in engineering concept, this gives a finite amount. But when you instead of 0, you make a slight increase in your, this is say some value you will have here, then obviously you need, if you want to maintain this flux constant, then you need mmf that is greater than 0. Now here it is interesting to note that again and again I am mentioning this, that if your supply voltage and frequency remain constant, your transformer will act as a constant flux machine. So when you will have a low reluctance value rather than having zero reluctance, then what will happen? A magnetizing current will be drawn, and that value of magnetizing current or no load current will be having some finite value. Previously I naught was 0. This is previous case. Now we are having I naught that is greater than 0. And greater than 0 means although I naught is a very big or very large current, but I naught is something that is means you can't neglect I naught anymore. That is my point, because your reluctance is not equal to 0, and remaining things remain same. Here you have now the issue here is that you may argue, sir, as this angle is perfectly 90 degree, then what is the harm? Even previously I naught was almost 0, and now I naught is greater than 0. But if you see the input power consumption during no load, it is V1 I naught cos 90 degree. That is equal to 0. So there is no harm, apparently there is no harm. Still the transformer is not drawing any real power from your source. The answer is that there is a small problem. Here I have started my discussion telling you that the transformer is ideal. However, I have no way claimed that all other elements present in your system, they are ideal. Suppose you use an extension cord to connect your transformer with your source, and that extension cord, although having a very small value of conductor resistance, its wire is having a finite amount of resistance. Now, when your transformer current I naught become greater than 0, then the connecting wire that connect your supply with your transformer primary, there will be some copper loss. More interestingly, what about the change when we consider this transformer with non-zero reluctance with some low value of reluctance and some finite value of magnetizing current. What about the transformer phasor diagram when we load it? See, this is your V1. Now you are having this I naught. This is your E1, this is your E2, this is your I2. This angle is your load angle. Now, what about the primary current? E2 is equal to N2 by N1 E1, fine. And accordingly, you will get a reflection of this I2. You may call it I2 dash. Now, till this it's okay. But unlike previous case when you had I naught almost 0, your I1 in the previous case it was just magnitude and phase wise it was previous case. But now what is happening here? If you want to find it out, you have to add this I naught with this. And how can we add that? Very simple. From the tip of this I2 dash, if this current is I2 dash, from the tip of this I2 dash we have to draw a line that is parallel to the line of I naught. Well, and then you have to connect. Then you have to connect. So this one gives us I1. Now see the change. Previously, your in case of ideal transformer with zero reluctance, secondary PF and primary PF was equal, but right now your secondary PF is greater than your primary PF, or stating other way, secondary PF angle is less than your primary PF angle. That means now your transformer is operating, the primary of the transformer is operating with a poor power factor than that of its load. If the load power factor is 0.5, then it will operate with a power factor of say 0.4 or 0.3, something like that. So that is not a good indication for a transformer, and that whole thing is coming due to this consideration when we remove that idealistic assumption that reluctance is very small. Now let us consider what will happen when in no load, when we will consider there is a say there is a hysteresis and eddy current loss. What was the another part? This is actually our assumption 2. What was our another part of assumption 1, that we left untouched or unaltered, because if we alter, then we will not be able to deal with that. It will become so complex. That assumption was here. Assumption that will leave unaltered was basically, you can say that is the assumption is that your transformer is a linear transformer and your flux is what is happening here? What color? Oh, sorry. There is a wrong color selection. Availability of too many options are sometimes confused. So that was assumption of linearity, that the transformer flux is proportional to the MMF. So although we are considering here hysteresis and eddy current loss, but we left that part, remains unaltered, that means flux and MMF, they are maintaining a linear relationship. Now the obvious question is that how to ensure it, or means in case of although we are assuming this, means we are claiming that this is an idealistic assumption, and of course it is an idealistic assumption, and means if we do not know how this one is valid in real case, or if this is not valid, then what should we do? The answer is here. If we consider the transformer BH curve, I hope you heard about BH curve. I will also discuss it in detail in my electromagnetics. So, more or less, this is our BH curve. This area indicates the energy loss due to BH, means hysteresis. But this, we generally, this is what? This is our H, and this is our B, or flux density. And we know B is equal to that famous formula mu H, where mu is the permeability, and H is ampere turn per meter. So H indicates magnetic field intensity. It is not exactly MMF, but it is, as you can see, it is ampere turn per meter, so it is directly proportional to MMF. And B is the flux density. So of course you cannot increase the value of flux, or even if you increase the value of flux, if your core size remains constant, then your flux density will also become very high. But this BH curve, what we do in case of practical transformer, we will discuss it in our upcoming lecture also. That we try to realize this in this near this D point. We try to realize, so our voltage, our operating voltage and frequency produces a flux that keep B near this D point, and we don't have to drive to this saturating region. So that is why this assumption, we try not to violate this assumption to a great extent. So if violation of this assumption takes place, then we will have difficulty in calculation and understanding. Although the violation of this simplistic assumption is inevitable, and we will see what kind of treatment we can do, how to avoid them, but that is an advanced course of study. In our syllabus it is there and we will discuss, but not now. So if that is the case, then in a nutshell what I was trying to say, that these hysteresis and eddy current laws, we will consider them that as if they are not making these things, we will treat them as lossy element, but we will not consider like hysteresis and eddy current. This hysteresis effect is itself a non-linear phenomenon. But what we are doing here, we are playing a very clever tricks. We are not trying to realize that hysteresis or that non-linear characteristics during our present analysis. Rather, we are claiming that whatever that non-linearity cause a power loss, we are representing that power loss by means of a resistance, and we termed it as core loss resistance. So what I am trying to say here, lossy element, but we will not consider them as non-linear element present in our system. So our basic objective is to replace hysteresis effect by an equivalent resistor or that can in equal amount of losses. So do remember, core loss resistance is a virtual resistance. Is a virtual resistance. It doesn't exist in reality. It is just a representation, a linear representation of actual nonlinear phenomena. Now, Obviously, when we are talking about loss, we have already said that this will be so. In my based on my discussion that having non-zero reluctance, our equivalent circuit of the transformer as of now has become like this. We are considering only no load. Later on, we will consider how it behaves with full load. So, now the question is that how to hysteresis loss. So, we are replacing, means we are trying to have a linear approximation, and that approximation obviously when we are talking about loss. For power loss or for any kind of power loss, you need a resistance. So if resistance is required, then the another question, obvious question will come, whether we should, now this is like an ideal coil. Now whether we should insert that resistance here. This is due to that core loss resistance, let it be R naught. Let this one be X naught. X naught is our magnetizing reactance. Previously, magnetizing reactance value when reluctance was 0, what was the value of your magnetizing reluctance? When reluctance in previous case was almost equal to 0, what was the value of your magnetizing reactance? You have to answer me. This is a basic question that in our previous discussion we said that magnetizing, suppose this coil was there, then if my reluctance is almost is equal to 0, then what is the value of its magnetizing reactance? Now our reluctance, at present we have removed this assumption that reluctance is not 0, so this is our magnetizing reactance and it is having a finite value and that value is X naught. Now we are proceeding to the next stage, where we have to consider the hysteresis loss and eddy current loss in our account. And hysteresis loss, eddy current loss, all those loss clubbed together as core loss or iron loss of a transformer. And that iron loss, what we are doing here, we are trying to approximate them by a linear element and try to represent it in our circuit. As it is power loss, we need a resistance. Neither capacitor nor inductor will serve our purpose. Now the question is that should we place that resistor if this R naught is our core loss resistor? Obviously this is a virtual resistor, but it's okay. So what to connect that virtual resistor? In series with our magnetizing reactance or in parallel with our magnetizing reactance? In order to answer this question, the right answer is that we have to connect it in parallel. But why should we connect it in parallel? Because it is there in the book. Because since 19 means early 19th, people are means representing it like this. The first book on electrical machine was written probably on 1905. So you will say that people are representing it like this. So the hell we are to order this convention or this representation. But we are someone and our values count, means our difference in opinion should count if we can present something logical, some logical argument. Here the convention comes in this way. In order to understand the placement of R naught in our circuit, whether series or parallel, we have to analyze the nature of hysteresis and eddy current loss. Hysteresis and eddy current loss also known as core loss depends on two factors. One is voltage, another one is frequency. Our experiences, and if we can keep these two quantity constant, then for a given coil, its iron loss remain constant. It is very important to note that if we keep voltage and frequency constant, then that will ensure our core loss is constant. Now the very important understanding here is that if vice versa, if you change your voltage or frequency, then your core loss will vary. But it has nothing to do with the inductor current, whether the inductor is carrying 1 ampere or it is carrying 1 mega ampere. It won't change the nature or the loss, not nature, the loss occurred in that circuit. The iron loss occurs in that circuit. So, we must understand, if we connect something in series, say R naught in series, then what will happen? You are having X naught here, you are having R naught. Now, suppose you place it in series and then there is a change in series current, like when some more current will be flown through that inductor. Obviously, if you connect it in series, it will have this hysteresis and eddy current loss, that core loss, will start varying with load. Means had we placed this R naught in series, then the core loss would have started following the loading of our transformer. If we load more, then core loss will increase. If we reduce the load or remove load from the secondary, then core loss will should also reduce. But in reality, core loss remains constant, and also that is why sometimes we call it constant loss, because as long as if you keep your voltage and frequency constant, core loss also remains constant. And that is why we should understand that it cannot be placed in series with our magnetizing reactance. This component that we are trying to insert in our circuit to make a linear approximation of some nonlinear phenomena that causes also some power loss in our circuit. We cannot capture that nonlinearity or cannot represent that nonlinearity, but we can have an element, a linear element, that will represent our nonlinear things here. So, with this, let us see what type of changes will occur in our phasor diagram. So, changes that will take place. Previously, it was your only X naught, and this was, now here you have inserted one R naught, and here it is your voltage. Now, if this no load current was I naught, then we can, now as we are having two parallel branch, we can say I mu is the magnetizing current and I H plus E is the current that is flowing through R naught. So, if somebody asks us to draw the phasor diagram, it will be like this: V1, then you are having, this is my I mu, and also you will have one more component here, that is in phase with your voltage, that one is IH plus E. So what is your resultant component, resultant current? Resultant current will become this is our I naught. Now previously it was 90 degree lagging. Now there is a change in angle, and that change is in positive direction because we are traversing in anti-clockwise. Like this, if this is our theta double dash, and if the previous angle was theta dash was 90 degree, and theta double dash being an acute angle is less than 90 degree. But this change takes place, means I naught phasor shift in counterclockwise direction. So this means change of orientation of I naught in counterclockwise direction, we call it as this angle, this we can write theta double dot plus alpha is equal to 90 degree, and this alpha, hysteresis angle of advance, is this alpha. Here this is my alpha, right? And the other part remains same. Like here we will have minus E1. So unlike the previous case, now some loss starts taking place here, and that loss you can either write V1 I naught cos theta double dash, or you can write V1 I naught sin alpha is equal to your no load power loss, or P naught is equal to your load loss, right? Now we can draw phasor if we load it, but that is not required. Now let us move to the second part. Now let us move to the let us consider. I am going to remove that 3 and 4 both together. What was there in 3? Okay, let me remove that restriction 3 first. 3 was restriction 3 was no leakage flux. And right now I am going to discard this assumption. So whenever there will be a leakage flux, that means, first of all, let us try to understand what is a leakage flux. Suppose if you have two winding like this, they are proximity of each other. You have mutual flux that link both the coil. These are the mutual flux that links both the coil, and when the coils are, means whatever variation is there, they causes induced EMF, same amount of induced EMF. Now, in case it is that leakage flux is there. So what is leakage flux? A leakage flux is like this. It starts somewhere but doesn't link the other one. So this is an example of leakage flux. Now what is the problem with the leakage flux? If your obviously if there is leakage flux, this will also produce some leakage flux. Now the problem with leakage flux is that when we are talking about leakage, so in order to represent that leakage flux, first of all we have to think that whether we need resistance or better to say a resistor or an inductor or a capacitor. The right answer is that as it is related to flux and flux leakage, it should be inductor. Now again we'll have a bit confusion regarding the placement of that component. Like if it is an inductor, then it will have an inductive reactance. We call it popularly as leakage reactance. Now we have to decide that in our model, which was our equivalent circuit model, which was like this, after considering hysteresis and eddy current loss, shall we place our leakage reactance, if we consider it as XL here, or we should place it here in series? The correct answer is that we should place leakage reactance in series. Now again the obvious question is that will come, that is why? Why we should place it in series? See what is happening here in case of leakage reactance. When you have a leakage, your flux that is produced by the primary winding cannot link with the secondary and vice versa. Now until unless your where this will come in the picture. Suppose there is no node connected across your secondary. So if there is no node, no current will flow through your. I might be sound a bit confusing, but let us try to understand. That secondary is linked with the flux, and that flux, amount of flux, is somewhat less than that of primary. So if that is the case, as long as we don't have leakage reactance, what is our transformer equivalent model? Here it is our primary terminal. We have primary, and here this side is our secondary terminal. Now, when there is leakage, how leakage will affect us? If this primary winding, what is there? It is producing some voltage, and your flux or that is proportional to your supply voltage and frequency. Now, if this is the case, now consider a situation when you connect a load across your secondary and there is some leakage. So here you have connected your source and your load but there is some leakage. Now this leakage flux will surely cause a reduction in your induced yield. Why? Because it is leakage, it can't link with your both the windings, and it is our primary assumption that whatever means we will when we will try to when we so it is our fundamental understanding that when we will try to represent to your equivalent circuit, then here we I hope you have already done it in your basic electrical engineering that secondary referred to primary and primary referred to secondary. So what we used to do here, that only one voltage, a common voltage should appear across this, and that common voltage, obviously when we are talking about leakage, then the effective amount of voltage across this branch will be surely less than that of the previous case when there was no leakage. Because if your secondary winding, when we are considering two windings separately, you will see that if only the red lines are present. Do remember the flux production is due to this V, but a few flux lines fail to link with the secondary. So therefore, here the voltage amount will be somewhat less than that it should be. So in that case, in order to represent what we need to do, we should consider something that is responsible for our leakage. But if we want to think about this, then we have to think when our secondary actually comes into account. Until unless there is a this current flowing through our secondary, then whether there is a leakage or not, that we will not able to understand. Because until unless we put a load across secondary, then only we will realize that whatever useful amount of flux that primary can utilize, the secondary is getting deprived of that. And when you, more importantly, when you connect the secondary with a load, secondary will produce its its own flux to means oppose primary flux, and at that time also secondary flux or the secondary side flux will not link with your primary side flux. So this whole thing is not, we will not able to visualize until unless we connect a load with our secondary side. And more importantly, that what we will observe that this amount of leakage is increasing with the amount of load. If we put more load, then there will be more number of leakage flux lines that do not link both the windings. So therefore, as leakage is this leakage reactance, it is proportional to the or leakage, better to say not leakage reactance. What happens to this? This leakage flux is proportional to the load current. And what is the effect of this leakage flux? Leakage flux cause a reduction in induced EMF. So if that is the case, then only when secondary is loaded, then only we need to consider the leakage flux, and obviously we will place it in series with our previous equivalent circuit with no leakage flux, and we are considering that leakage flux are we consider this XL2 dash, if this is the primary one, this is R naught, this is Gx naught, this XL1 is equal to XL2 dash. That means leakage reactance is equal, or amount of leakage experienced by both the sides are equal. Now the interesting thing to realize that how our phasor diagram will be affected due to this. So in order to understand that phasor diagram the problem, we have to connect one load across this. And here we have our source Vm sin omega t. So with this, let me draw the phasor diagram. That is, with this, let me draw the phasor diagram. Again, I am considering our V1 as reference. So if you consider V1 as reference, okay, one way you can do that right now, as we are considering the load, we have connected load. So let us consider the voltage across our secondary side is V2 and the current is I2, and this is our load power factor angle. This V2, I2 and this power factor angle you can measure using an wattmeter. Wattmeter and ammeter you can measure. This one is theta 2, this is load power factor. So I have drawn this transformer once again for our better understanding and clarity. This is our load. Across this load, if we connect a voltmeter, the voltmeter gives us a reading V2, and if we insert one ammeter here in series, it will give us I2. So with this, we are ready for phasor diagram, and also if we can connect an wattmeter, then from that wattmeter reading we can find out the power factor. So from this we can find out the power factor angle. Now here, this is instead of in earlier cases we used to draw phasor diagram from primary side, but now we will try to draw it from secondary side, because drawing it from primary side will not be that easy. So in secondary side, if we consider the secondary side voltage before means clubbing this equivalent circuit, when there was two separate circuit, like first let me draw the secondary side only. This is our equivalent portion of secondary, and voltage here is E2. Here the reactance is JXL2. Why it will become XL2 dash? When you will refer it to the primary side, it will become XL2 dash, and accordingly this will become, actually I should not draw it in this way also, because this will be a bit misleading. Yes. Why misleading? Because here actually whatever by this referred circuit you will get actually here V2 dash, and here the current will be I2 dash. So before going to that, let us consider here there is a separate, means electrical isolation is there.
in equivalent circuit there is no electrical isolation, but in means physical circuit or in practical circuit there is electrical isolation. Here you have your primary coil. I am not considering that primary side first. This is your primary, not R not here, as we have separated these two. So this is our primary. At present I am not interested with primary, so I keep it off. I am only dealing with secondary. So if we try to write the equation for secondary side, then the voltage across this is V2, the current is I2, then what is E2? E2 is equal to V2 plus JI2 X2 L2 JI2 XL2. Now what is the angle between V2 and I2? Between V2 and I2 angle is theta 2 and it governs by load. Now let us first draw the phasor diagram of E2. So what is E2's phasor diagram? E2 is equal to V2 plus J I2 XL2. So let us first draw V2. Let us consider, as we are dealing with secondary side, we will consider the secondary voltage as our reference. Now this is V2, then this is our I2. This is theta 2. Now we have to draw JI2XL2. Here I would like to mention that I have often noticed that quite often students get confused that how to draw a phasor or realize this phasor addition. Here I2, this one is having orientation same as, if you discard this J, what I am trying to say, if you consider only I2 XL2, they are having orientation parallel to your I2 line. Like this. Now this is means if you extend the phasor of V2, you will see this angle is also theta 2. By virtue of geometry, this is theta 2. Now here we have to draw JI2XL2. Now in order to draw that JI2XL2 here, what we should do, first of all, magnitude of I2XL2 you have to find it out, and as this is a voltage, you have to scale. Like if this is V2 is 100 volt and you have dedicate a certain means you have defined one small unit of your graph is equal to this, then obviously according to that you have got certain length for this one, this 100, this is a 100 volt, this is a phasor corresponding to 100 volt. Now if you find this is 5 volt, then this should be exactly, if this phasor length is say 20 unit, this phasor length should be 1 unit, and accordingly you get the magnitude. Now what about orientation? It is multiplied by J. When there is J means there is a 90-degree phase shift in positive direction. So how can we traverse in positive direction? JI2X2. So here from this line we have to rotate 90 degree in counterclockwise. So this gives me Ji to XL2. Now, if you join the tip of Ji. Now seems you people are quite confused, so let me write down all the equations once again, one by one. Equation number 1, V1 is equal to minus E1 plus J I1 x L1. Equation number 2 is E1 by E2 is equal to N1 by N2. Equation number 3 is I1 by I2 is equal to N2 by N1. Equation number 4 is E2 is equal to V2 plus J I2 x L2, right? Then I have a bad habit of making mistakes of means capital and small. Don't get confused. Obviously you can ask me later on. So this now with this what we have our I H plus E is equal to minus E1 by R naught I mu is equal to minus E1 by Jx naught. This is all the equations that we have here, and also equation number 7, I naught is equal to, actually the correctly equation should be like this, N1 I naught is equal to N1 I1 plus into I2. And from this, if we proceed a step further, we will get, it will lead us to I naught is equal to I1 plus N2 by N1 I2. Now, in case of a transformer operating with certain load, you can measure load current. That means you can measure, this is our load current, you can measure it. And I naught is a constant current for constant supply. But there is, I1 should be found out. So how to find out I1 from this? I1 is equal to I naught minus into N1 by I2. That is what we write it like I0 minus I2 dash. And always I have drawn minus I2 dash there. Now here with this, let me redraw the phasor diagram once again so you can understand it clearly. It was V2, then we had I2, this is theta 2, Then we got E2 is equal to what? E2 is equal to V2 plus JI2 x L2. So we draw a line from the tip of V2 that is parallel to I2. Then from that line we draw another line making an angle 90 degree. And when we join them, we got E2. Then what we know that E2 and E1, they are in phase because they are produced by the same flux linkage. Okay, and now one more thing here I would like to mention, that don't get confused with polarity. Polarity I will discuss later. So E2, E1 will be in phase with E2. This is my E1. Now once I get my E1, then I can also draw minus E1. This is my minus E1. Now once E1 and minus E1 is over, then what equation? This equation we have to take care of. So I2, how to find out I2 dash? Here this is my this is I2, this is I2 dash, right? Or rather minus I2 dash. Then with this minus I2 dash, what we should do? We have to find out I0. How to find out I0? There will be two components. One is IH plus E. Another one will be lagging minus E1 by an angle 90 degree. So we have to traverse in clockwise direction. So this gives us the direction of I0, and when we obtain the vectorial addition of them, first let me draw this TD I0, then we will draw I2 dash. This is my minus I2 dash, and this is my I0. Now how to find out I0 minus I2 dash? So this is minus I2 dash, just we have to place I0 here. So this is our I0, and when we will join them, they will give us our I1, and based on that I1 we have to draw JI1x1. So JI1x1 is our I1. JI1x1 should lead this line, that means it should be 90 degree counterclockwise. So this is my now if we join this this will be V1. So primary power factor is between these. This is our transformer primary power factor. It is not same as theta 2, so this is a practical transformer. Now we have to remove that last part, that winding conductors having finite resistance. I ask you to think about it. First, the placement of the element that will represent the winding conductor resistance, and the second, what is the modification required for this Phasor diagram. So as of now we have removed 3 restrictions. Last 4 restrictions should be removed by you, and you have to draw first you have to determine the placement of that element, and second you have to draw the corresponding Phasor diagram for it.